of row differences. Why don't you try this one and see if you can do this one with regression, because this will be another layer for you to deal with. And I'll come back to you later on that, or we'll go through that in class. So for the next part, we're going to do the mathematical induction. We want to show 4 things. And we can go through that in a minute, but I want to show you the concept first. So if I have this example here, here's a sum formula of the odd integers, positive odd integers. This is the general rule for the odd integers. So if I plug in 15, I'm going to get 29. And so that's another odd integer. And if I look at this side, this is what the sum is equal to. Now, how do we make that generalization? Well, what happens is that we can look at patterns. And so if I see some patterns here, I have the set of odd integers here. So if I do a sequence of partial sums, I take the sum of the first term. That's just the first term there, which is 1. Oh, that's 1 squared. Okay, that seems to work. If I take the sum of the first 2, 1 plus 3, that would give me 4. Sum of the first 3, 1 plus 3 plus 5, that would give me 9. Oh, it looks like this pattern holds true. So what we want to talk about is this right here. And you don't have to write this part down, but this is the idea. I want to prove that this is true for all n. Now what happens is that a lot of times these patterns might work at the lower end of the scale, but later on they won't work. So what happens is that through mathematical induction, the concept is if we establish that it does work early on, then we can prove that the next term works. Well, that means that for the next term and the next term and the next term, all of those consecutively will work. And so when we prove this in general, we want to take a kth term and work on the kth term to prove that. Now, this might be a little bit confusing right now, but we'll try to show you what happens here. So if you look at this, the things that we have to show, that the equation holds true for some initial value. So we have to establish a pattern. Then we want to assume that this equation right here, in terms of k, is true. And why we do that is because we have to in order to prove this. It just doesn't link up otherwise. Then the third thing you have to do, and this is where it gets kind of algebra heavy, you want to show that the k plus 1 case does work. So you're going to have to plug in k plus 1 sometimes to 2 sides of an equation to make it go. Then you'll do the algebraic manipulation to get it to work. The last thing is to write a conclusion. So we're going to do that now. So we can answer this question: does s sub n equal n squared for all integers n greater than or equal to 1? So the first step is show that this works for n equal to 1. You could show it works for n equal to 2 or n equal to 15, but you have to lock it in someplace, and then subsequently after that point, that's what we're trying to prove, that it works for all those other values. So if I show that this works for n equal to 1, what I do is I take the sum of the first term. So that would be s sub 1 is equal to 1. So we took s sub 1, which is just this piece right here, which is 1, and we want to show that that's also equal to what happens on this other side when I plug in 1. Well, does this equal, and I put the question mark next to it, usually we put it above, but we want to see that this is equal to 1 squared. So we write out the 1 squared, even though it's obvious to us. And is this true? Yes, absolutely, that 1 is equal to 1. And so you check that off, saying that, okay, yes, this does work. Or you can write, yes, n equal 1 is true. So we found a basis for us to start. If we can't find this basis, then we can't start this. Sometimes you have to go past 1 to get something to work, but they'll try to indicate that that is true. So this is the first step for you. The second step is kind of but what happens is that we want to assume that s sub k is equal to k squared is true. And why this is because we're kind of taking a part way point in this sequence, and we need to make sure that we know that that does work. Well, you could plug in 15 or different things, and yeah, it does work. Okay? But this assumption has to be assumed, being redundant, but it has to be assumed in order for us to prove this. Okay? So by the assumption in part 2, we need to show that the sum for the k plus 1 term is equal to k plus 1 quantity squared. So in other words, I'm taking this n and I'm replacing it with this next term. So here's the kind of the tricky part. What happens is then is I have a sequence 1, 3, 5, 7, and 2k minus 1. I'm doing it in k now. That's identical to what I have right here. What I'm doing then is I'm upping it by one more. So I'm taking and I'm placing one more term past this one right here. Well, it's in terms of k now, 2k minus 1. To go one further, wherever I see this k, I'm going to take it out and replace it with k plus 1. So all I'm doing is showing that I'm adding in one more term. And that's what I've done here. And then on the other side, I also said, okay, if I add in one more term on this left side, I need to bump this up by one more term as well. So then that's where the k plus 1 on the right-hand side comes from. So really, this is identical to what you started off with, but I added one more term here, and then I adjusted this one, the sum formula, to be one more. And now all you have to do is the algebra to sort this out. But there is one trick in here, and that's what we have to take care of. To simplify this, we need to look at this sum right here. And with this sum, we know what this is because we've assumed it. We've assumed that the sum of 1 plus 3 plus 5 plus 7 plus 2n minus 1 is equal to n squared. So if I change this all over to k's, which is what I have, this is equal to k squared. So in the black here, this whole thing turns out to be just k squared because that's based on my assumption. That's why we assume this step number 2 right here. Okay, so that sum is equal to k squared. Well, that makes things pretty easy for me now. So since this thing in the black is all equal to k squared, then I do plus, and then I simplified this thing in the red here to 2k plus 1. And then I want to show that that is equal to k plus 1 quantity squared. So now it's just the algebra here. Well, this one isn't too bad. K squared plus 2k plus 1. And you should get this side equaling the right side like we did with other things before. You just work on one side. And I factor this, k plus 1 squared is equal to k plus 1 squared like that. And so we do have equality. So we've just verified that this does work for the next term. So we showed that it worked for n equal to 1, and then we're going to show that now it does work for the next term. So this is proven because of both those facts. And we have to state that now in a conclusion. So, and finally, we say the conclusion, since we have shown that S1, the sum of one term, and S sub k plus 1 hold true, both this holds true and this one holds true, by mathematical induction, we can conclude that S sub n is equal to n squared for all n greater than or equal to 1. And when we talk about n is going to be an integer, positive integer, and so that's what we're looking at. So once again, in summary, we have n equal to 1. S sub k is equal to k squared is true. Then we assume that, and then we need to show that the next term case holds true for both sides. We verify with some algebra, and then we write our conclusion. Okay, for part B, remember the steps that we have to do. So this one changes. I still have that in there. So for part B, we're going to use this format. Show n equal to 1, and then we're going to assume that this is true. This is just a blanket statement, or just one statement for us. And then this part 3, we need to show this. This is the algebra part, and don't forget your conclusion. Okay, I'm going to go to the screen part of this so that you can see this a little bit better as I do it. Okay, so here we have this. We need to prove that this works for n equal to 1. So we do S sub 1 is equal to just that first term. Well, that's 1 squared. The question is, does that equal when I take 1 and plug it into this? So it's 1 times 2, and then that would be 3. So I get a 6. 6 over 6. Does that equal 1? Yes, that does. So I have a situation where 1 equals 1. So now we can go forward. We've established that this pattern does work for at least one value. Then we go under the assumption that this works for all these terms, or for a k term. And then we have to show that it works for the next term. So I already printed this in here. wherever I took or had the n, I put in a k plus 1 on the right-hand side. This left-hand side will be the sum that I'll write here in a second. So overall, and then I simplified it here too. So what happens is this, is that I have 1 squared plus 2 squared plus 3 squared Okay, so those are the terms that I already have. I got to go one more. So I took my original here, and instead of stopping here at k squared, I got to add in one more term. That's what I did there. And then for this top is equal to, I have it written here, I added k plus 1 wherever I saw the n for my original right-hand side here. So when I do this, this is what I have to show through the algebra. Well, the trick again, what do I replace this whole thing with? Not this last term, but all this. Well, since I assumed that this is true, I can replace this with k plus 1, and then 2k plus 1, all over 6, plus my k plus 1 quantity squared. And does that equal, and that's what I'm asking with a question mark, does that equal whatever I have here? So what I'm going to do is I'm going to go through, simplify this, and then I'm going to talk about what I did for a moment. So the first thing I did was I got a common denominator. Then I got this situation right here, all over 6, which is what I like over here. I try not to manipulate this side, so I have to make this side look like this side. Well, what's in common between this term here and this term here? Well, I see the k plus 1 is kind of screaming at me because I do have a k plus 1 over here that I do need. And so what happens is if I factor that out, here I'm left with a k and then a 2k plus 1. And then here I'm left with a 6 and a k plus 1. So I just took one of the k plus 1s out. And if I try to simplify this now, so if I factor out that k plus 1, I get this. I simplify the inside, so I just distribute, and then I combine like terms, and then I factor. And so this inside part, I get this portion right here, which is identical to over here. Don't forget that I had it over 6, so I was just simplifying the numerator here. Everything's over 6, and so that does work. Then your conclusion, you write, since the S, it's pretty much the same sum formula as what you did before, so you write that for your conclusion. All right, the other two formulas you can probably do in class. This is getting a little long, and so we're going to leave those two for class. Thank you very much, and have a great day.